Okay, so over on Facebook, somebody was asking about dodecahedrons and how to make them in CAD. And I wanted to start with a demo of what I mean. This is going to make more sense in a second, but trust me. Okay, so if you had this in your hands, from this point up here, up at the top, to down here, this spans a 180-degree arc. And there's an axis that passes through here down to here. And when we slice this in half, we actually get our arc passes through the midline of this pentagon and passes through the midline of this pentagon and passes through this edge. So we can model that actually, and we don't have to ever mess around with dihedrals. You don't have to look up anything. This is what I've been doing for a while. It's very straightforward once you kind of get the hang of it. So we're over here in Onshape, but this should work in other software. The idea is we are making we are pulling some geometry that is out of plane back into plane, and we are doing that with the solver instead of, I've done this with revolves before, but it gets a little hairy. What is common between each of these faces and each of these edges is that they are perpendicular to the origin. So I'm just applying a perpendicular constraint. Let's go and make another one. This is not going to make sense for a second, but like, please trust me. So back to this over here. See how these two pentagons are joined at this edge? We could, if we wanted to solve for the path that these go through, we could spin these with like a revolve or something. But what we're going to do is we're just going to glue them together with a coincident at the midpoint of these two edges, and we get that the height of the midpoint for free, basically, because the solver already knows what a pentagon looks like, and we don't have to mess with 3D sketches. And this is going to make more sense in a second, but what we're doing is the sketcher is gonna try to like make some constraints that you don't want, but the basic thing, what you basically want, and this looks like a mess right now, but what we do is we take, okay, so this edge, remember, we've got an edge, we've got a mid plane, the mid face edge, and this midline mid face edge, this mid face line here. And when you set the equality to this one, and this one, and then we make it stretch over a known distance. So let's make this one vertical, and watch what happens here is as we move this, yeah, okay, and we can see that this one still needs to be set perpendicular. But watch what happens as we move this. So see how these all kind of hinge together? This works for whatever geometry we want, whether that is we are spanning 90 degrees or 180 degrees, as long as we know the angle between the two. Between the start of our path, say the start of our path here, at this top tippy point, across this midline, down this edge, we can use the solver to be like, okay, what is what needs to happen for that to be true? I'm just setting some sketch, some construction geometry. Now this still is all all this still is all blue. This is still all undefined. But what this is showing us is that there's only 1 degree of freedom here. So if we take a circle and we go out, so this is, I'd be tempted to go here, but it's really, we want actually here, because this is where multiple points want. And if we want a dodecahedron where the outside edge, if you hold it between the 2 points, that diameter is a certain amount. Let's just go 200 millimeters. But now notice that this all just locked in from 1 dimension. I can change this really easily. If we really need to know this instead, if we want our edge length to be something, right now this is a driven dimension, but so this can be changed. This is dependent on this one. Oh, now it's 70 something. Like, finding that by trial and error would be really difficult. Okay, but here's where the cool part happens. We're gonna take a plane on this here. We're gonna do a line angle, so we just need 2 things from the plane. We're gonna pivot it around here though. So let's make this a 90-degree line angle. And then let's do it the same for this one. Let's make a line angle off of here, 90 degrees. So you're like, okay, so now we've made a bunch of sketch geometry. Like, what are we even doing here? But bear with me. We're going to do a sketch on this surface. And we are going to do another polygon. Make sure it's a 5. We're going to stick this to here with a coincident. And now look, it's nice and locked in. And then we're going to do that a second time. Hide this plane. We don't want to look at it. And make sure we're selecting 2 things. I don't think you necessarily need to select 2 things, but it makes it really clear what angle we are pulling from. And then we're going to do a sketch on this plane. We're going to do another polygon. I'm going to glue this. I keep saying glue, but we're just coincident. This to this, this to this. And since we already defined the height of this pentagon elsewhere, that is solved and known. Oh, I hid this sketch. Okay, I meant to hide the plane. Let's hide this plane. And what I like to do here is you can do stuff where you extrude this top face. I'm actually going to go and make this line some construction geometry, so we don't have to make a messy extrude that might get chopped up if we change something upstream from it. Now, I really like doing a loft. We take this face and we loft to a point. Make it a solid. Cool. We're going to do this one. We're going to loft this one to a point and make sure this is new, not adding, because then they'll glue themselves together and it's hard to separate them later. And now, okay, you're like, okay, so we have 2 faces, but it's easy with mirrors and circular patterns to kind of, for lack of a better word, propagate these little prisms down to the other side. And you're still probably asking, like, why would you do it this way and not just like input an angle and not have to just go through all this trouble? And what you get out of this, and I think this is really important, I've been bashing my head against this problem for like a decade, literally, is since it's all done in the solver in a language that it understands, by the end you get geometry that is vertex perfect, that there's no error for it to get messed up on. Okay, so what we just did is we took this kind of prism here. Let's hide this sketch. And we spun it around 5 times, copied it around this one. We made those axes that were kind of perpendicular to the face, the normal line. And this fun trick here, we can just go sketch, midplane of this one, and I've done a bunch of this stuff, so it's like, you can try different stuff. It's easy to just try and see what works. But what I'm trying to do here is just do a circular pattern on that little axis that we just made. And ooh, that's cool. Okay, so there we are. We're at like, I don't know. So yeah, that's we get that for free. But since it's solid and it's vertex perfect, I'm not sure what else to call it. We can do wild stuff like this too, where we're gonna like, oh, I'm gonna make a circle that's like off center, and then make a axis so I can revolve it into existence. This is vertical. Just trust me here for a second. Revolve. Let's just hide these parts for a second. And then we're actually going to do a, yeah. The idea of what I'm doing here is we are trying to kind of do a Boolean operation of this revolve axis, this intersect, merge with all, and we can get wild stuff like this where we have a asymmetric spherical projection of a dodecahedron for basically free. And this is, if we do a section view, we can see that like there's no interference. And if we select all our parts and we do interference analysis, we get no interferences. So you'd think that you'd be able to do it just with like floating point numbers, or like looking up the dihedral on Wikipedia or whatever, but what happens is that those errors build up over each additional face that you've copied that error over, and by the time you get to the full other side of your polyhedra, those have all added up, and the faces no longer line up. But when you base the geometry in something that the solver understands natively, is just thinking in, for I don't know. There's no opportunity for it to build up those floating point errors. So this sounds like a lot more work, but like once you're decently practiced at it, you can just spin up a polyhedra in a couple minutes, and like that has enabled me to make some really cool stuff. Thank you for watching. I have a couple other videos on this stuff, but I hadn't specifically made one on dodecahedrons, so just going to suppress this for a second so we can see, hide our lower planes, hide our sketches, and yeah, now we have a dodecahedron. And we can do whatever we want with this. We can do shells, we can do, let me just get all this geometry for free. So, okay, I've talked too long, but thank you for watching, thank you for listening. I love answering questions. This is one of my favorite things, so thanks.